Hi all. Today we discuss section 6. This session deals with the cyclic groups. The last class we have defined cyclic groups using the cyclic subgroup generated by an element. That means say belongs to G. We take this is the cyclic subgroup generated by A. This consists of elements a raised to 0, a raised to 1, etc., a raised to 2, etc., a raised to minus 1, a raised to minus 2 are all in this way. We write this as, in that theorem we have denoted this as capital H, and we have proved this is a subgroup of G, and in fact this is the smallest subgroup of G containing A, and this subgroup is also called the cyclic subgroup. The cyclic subgroup generated by A, the element A, and in this case we have defined as the generator if this cyclic subgroup generated by A is whole of the group G. Okay, so in this case this G is called the cyclic group. This is the definition of cyclic group that you have seen in the last class, and we say that this A generates the group G as well, and we can consider two different cases. G is infinite and G is finite. Before that we can consider the cyclic subgroup generated by A. Okay. If this cyclic subgroup generated by A is finite, if this is finite, we can say that the order of the cyclic subgroup generated by A is finite. Okay, that is the meaning of this. If this is the case, then we say that order of A is the value, the order of the subgroup. Okay, so using this idea we define the order of an element instead of order of a subgroup or order of a group. We have already defined what is an order of a subgroup. That is nothing but the number of elements of that subgroup. If this is a finite case, we have already seen that in Z4 the cyclic subgroup generated by 2 consists of 2 elements 0 and 2. In this case we can say that the order of or the cardinality of the cyclic subgroup generated by 2 is equal to 2. Okay, similarly the order of the cyclic subgroup generated by 1, we have seen that this the order of the cyclic subgroup generated by 1 consists of all the elements of Z4 0 1 2 3, and in this case we can say that the order of the cardinality of the cyclic subgroup generated by 1 is 4. Okay, so from this you can say that order of the element, okay, order of the element 2 is 2 here. From this you can say that order of the element 1 is 4. So order of an element is defined to be the cardinality of the cyclic subgroup generated by that element, if that subgroup is finite. Okay, otherwise we define, order of A is infinite. That means the cyclic subgroup generated by A contains infinitely many elements, then the order of that element is infinite. Okay, so for example, if we consider Z is a set of all integers. We know that this is 0 1 2 3 etc., minus 1 minus 2 minus 3 etc. So this is our Z. We know that Z under addition is a group. In fact this is an abelian group, and if we choose an element 2 from this Z, Okay, 2 from this is it. This is the subgroup, this is a group, and we choose an element or any one of these elements from Z, and we consider that cyclic subgroup generated by 2. Okay, then this consists of the elements 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, etc. 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, etc. Okay, so here 2 raised to 0 represents the identity element of this group. If you are considering 2 here, then this 2 is the identity element of Z4. 2 raised to 0 is the identity element of Z4. Okay, but here this 2 comes from this group, then 2 raised to 0 represents the identity element of this group. So that is nothing but 0. And 2 raised to 1 is the element 2 in Z. So that is 2. And 2 square is the element in Z, that is 2, operate 2 times, that is 2 plus 2, since the operation is addition here. So this is 4. Here we are using usual addition instead of addition modulo 4. In Z4 we are using addition modulo 4. Then in this case 2 plus or 2 square is 2 raised 2 plus 2 addition modulo 4 plus 2. So this gives 0. But here 2 raised to 2 gives 4 itself, because here we use the usual addition in Z, and 4 is also an element of this set. Okay, then 2 raised to 0 2 raised to 3 is operate 2 3 times, that is 2 plus 2 plus 2, that is 6, etc. Similarly, inverse of 2 is minus 2 here, because minus 2 plus 2 is 0. So when you operate minus 2 times, we have minus 4, minus 6, etc. So this is the cyclic subgroup generated by 2 in this Z. Okay, so even though we are using this the same 2 in this case and this case, but since the groups are different, then the subgroup generated by the same element will be the different things. Okay, so in this case we can say that order of 2 is, from this you can say that order of the element 2 is actually that is the cardinality of this 2 if this subgroup generated by 2 is finite. So otherwise we write this order as infinite, because this is not a finite set. If this is finite, then the order would be the cardinality of that set. Okay, so this is the two different definitions for order of an element. We have now defined order of a subgroup as well as order of an element. Now we can now take inference from this. If this 2 is if the order of 2 is finite, then you can easily find 2 raised to here, 2 raised to 0 is 0, 2 raised to 1 is 2, 2 raised to 2 is again this 0. Okay, so when you observe these elements in the cyclic subgroup generated by 2, we can observe that there should exist a positive quantity, a positive number 2, such that 2 power 2 is equal to identity element. Okay, so that is another inference from this. So if this order of an element A is finite, then there exists, if the order of an element is finite, then there exists a positive integer m such that A raised to m is equal to identity element. Okay, so this is the nice observation from this finite group Z4. Okay, so in case of finite order, you can easily find out an element m, a positive element m, such that A raised to m is equal to E. That is because if you have if this subgroup generated by A consists of A raised to 0, A raised to 1, A raised to 2, etc., A raised to minus 1, A raised to minus 2, etc., then if this is finite, if this quantity is finite, we can say that all these powers of A are not distinct. Okay, there would exist two integers some r and s, such that this A raised to r is equal to A raised to s. If all these elements are distinct, then this subgroup would have infinitely many terms. Okay, but our assumption is this is finite, so there exists R and S such that A raised to R is equal to A raised to F S for some R comma S. Okay, from this you can write if R is without loss of generality, we can assume that if R is less than S, then A power R minus S equal to A power S minus S, that is equal to identity. That implies A raised to R minus M is equal to R minus S is equal to the identity element. So we can write this R minus S as the positive quantity, since this R minus we write this as S minus R, we write this is instead of taking R less than S, we write R greater than S. If this is the case, then we can get A raised to R minus S equal to E. So this R minus S is positive. The other case, if R is less than S, you can write A raised to S minus R, that is equal to A raised to R minus R. That is equal to again A raised to 0, that is equal to identity. This implies A raised to S minus R, that is positive here, which yield identity element. Okay, so if R is if order of A is finite, then if we have order of A is finite, then you have this result. There exists at least one positive quantity such that A raised to that quantity is equal to identity. Now we have a theorem, the 6.1 theorem, that is a simple theorem, comparatively simpler one. We have to prove that every cyclic group is abelian. So we start with for the proof we start with a cyclic group, let G be a cyclic group. Then if G is a cyclic group, then there exists a generator. So we let A be a generator of G, so that by definition of the cyclic group, this or generator, this G is same as the cyclic subgroup generated by A. Okay, so this consists of the elements A raised to N, where N belongs to Z. A generates G means the cyclic subgroup generated by A is same as G. The cyclic subgroup generated by A contains these elements, A raised to N belongs to Z. So if we have to prove that A is abelian. Abelian means commutative. That means we need to prove that A star B, that is AB is same as BA. Okay, so if we start with instead of taking A and B, we start with two general element G1 comma G2 are any two arbitrary elements, any two elements of G. Since this G1 is an element of this G, then that takes the form A raised to some R. Okay, so you can write G1 is equal to A raised to R, and G2 is equal to, again, that is an element of G. Then that G2 can be written as A raised to S for some R and S belongs to Z. Okay, now we evaluate the G1, G2. What is G1, G2? G1, G2 is equal to A power R, A power S. And we can evaluate this using the exponential rule, that is A power R plus S. And we know that since these R and S are elements of Z, this A R plus S is same as S plus R. Now you can write this as A power S, A power R, that is equal to G2, G1. Okay, so since this is true for every G1 and G2, we have capital G is abelian. This proves this theorem. So this is an important theorem, even though it is very simple one. It is very important theorem. Please note this theorem. Next we will prove the division algorithm for Z. This is the statement: if M is positive integer, please note this is a positive integer, that is very important, and N is an arbitrary integer, that is an arbitrary element of Z, then there exist unique integers Q and R such that N is equal to MQ plus R, and 0 less than or equal to r less than m. Okay, so we will easily prove this theorem, this result using if you take m belongs to positive integer, that means that is an element of n, and n belongs to z. Okay, then if this n is a multiple of m, then you can write this n is equal to qm equal plus 0 for some q and take r is equal to 0. Okay, if this is not the case, if this n is not a multiple of this m, then what happens, this n is, or n lies between two consecutive multiples of m. That means you can find a number q such that, or if you consider the real line first, this is our real line, and consider all the multiples here. M, this is 2m, and this is minus m, this is minus 2m, and all. And in this case we can consider two multiples q m and q plus 1 m, and then n lies in between them. Okay, if n is not a multiple of this m. Okay, so we write all the multiples here, and if n is not a multiple of m, then that will be in between these two multiples. Okay, so this multiple defines the unique q. Okay, so if we write this is equal to r, then we can say that what is this n? N is equal to qm plus r. Okay, and we know that this r is an integer, because this r can be written as n minus qm. N is an element of z, and qm is also a multiple of m, then that also belongs to z. Then clearly this quantity, this difference belongs to z. Okay, since this this n is greater than qm, this qm is the multiple which is the greatest multiple which is less than n. So this qm is less than n, then we can say that this is also positive. So this is these are all element of this difference is an element of z plus. Okay, that means r is always an element of natural numbers. Okay, so now if we have such two such numbers, for the uniqueness we assume that q1m plus r1, and suppose there are another expression for this n, that is q2 this is q2m plus r2. And one thing we need to observe is this r is always in between this r is always in between r is always positive or non-negative, and this is always less than q plus 1m and q plus 1m minus qm. That is because we know that this distance is always less than this distance is always greater than this distance. So that means r is always less than the difference between these two numbers, q plus 1m minus qm, and this is nothing but m. So if you set this as r, then this r satisfies the condition that 0 less than or equal to r. In this case 0 strictly less than r less than m. Okay, if r can be 0, that is the case where this n is the multiple of m. Otherwise this r always lies in between 0 and m. So if we have two such expressions, then we can expect 0 less than r1 less than m, and 0 less than r2 less than m. That means if we have a m here, that is a positive quantity, and suppose we have r1 and r2 in between these two numbers, then we can say that the distance between r1 minus r2 is always less than m. 0 less than or equal to the distance between these two is less than m. Okay, but from these two equations we can write r1. What is r1 minus r2? R1 minus r2 is n minus q1 minus m, that is r1, n minus q1 m, and r2, what is r2? That is minus of n minus q2 m. Okay, from this you can say that you can cancel these these two n's, and remaining will be q2 minus q1 times m. So that means that is a multiple of m. So this is a multiple of m that lies less than m. Okay, we know that the only possible multiple which is less than m and greater than or equal to 0 is 0. So from this you can write that difference is always r1 minus r2. This difference is always 0. That is the only multiple in between 0 and m. Okay, so this implies r1 minus r2 equal to 0, consequently r1 equal to r2. So this proves the uniqueness of r1 and uniqueness of this r as well. Okay, this proves our division algorithm. We will use this division algorithm to prove the next theorems. Next we will prove theorem 6.6. A subgroup of a cyclic group is cyclic. So we start with a cyclic group. Let G be cyclic. Let G be cyclic group with G is equal to A, cyclic subgroup generated by A. Okay, so this is the generator for this G. Then we need to take an arbitrary subgroup of G, that is if H is equal to a subgroup of G. If this H is equal to singleton set E, then you can easily write the subgroup is a cyclic group which is generated by E itself, because the subgroup generated by E consists of E only. Okay, E raised to 0, E raised to 1, etc. E raised to, these are all E itself. So we can say that this is a cyclic subgroup, or H is a cyclic group. Okay, and if H is not equal to E, singleton set E, then we would expect a non-identity element in this H. Okay, so H contains at least one non-identity element. That means let it be X. Then the exists X belongs to H, X not equal to identity. Okay, then this X takes the form X equal to A raised to N for some n belongs to Z plus. Okay, because first of all we can assume that this X is equal to X equal to some A raised to some R belongs to Z. If R is positive, then you can take this n as same as this one. Otherwise consider X inverse. Okay, so either X equal to A raised to R, or X equal to X inverse equal to A raised to minus R. We know that if X is an element of H, then this X inverse is also element of H. Okay, so we would expect this X belongs to H, then X equal to A raised to N for some positive quantity, this N. Okay, that means if X equal to A raised to R, then consider X inverse, then A raised to minus R, then you can get A raised to N as this one. Then we take minus R as the N if R is negative. Okay, otherwise you can take R is positive, then you can take R as this N. Okay, so if you start with a non-trivial subgroup of G, then there exists A raised to N belongs to that H with N belongs to the natural numbers or Z plus. Okay, now you consider this N, or we need to prove that this H is a cyclic H is a cyclic group. Then that means H is nothing but H is a cyclic subgroup generated by some element of H itself. Okay, now you take if A raised to N belongs to H, then we choose M. Let M be the smallest such number, be the smallest integer in Z plus such that a raised to m belongs to H. That means first of all we can get H contains an element, at least one element, a raised to n, for n is a positive number. Small n belongs to natural number. If such number exists, then choose such least exponent. Okay, m is the least such number such that a raised to n belongs to H. Now we will prove that H is a cyclic group. How will you prove H is a cyclic group? To prove H is a cyclic group, we need to prove that H consists of H is a group generated by some elements. Okay, so we let this a raised to m. Later we will prove that this a raised to m is the generator for H. That means we set C is equal to a raised to m, and we will prove that our claim is H is equal to the cyclic subgroup generated by C. Okay, to prove this, we start with an arbitrary element of this group H. Let B belongs to H. Then we will prove that this B is nothing but this C raised to something. Okay, C raised to some integer. Okay, so if B belongs to H, then B is equal to, again, since B is element of H, then that is a subgroup of G. Then B takes the form. Every element of this group G is nothing but, every element of this takes the form a raised to n, where n belongs to Z, because this A is the generator of G. So this B can also be written as B is equal to a raised to n for some n. Okay, now you write this n belongs to, for some n belongs to Z. Okay, now use the division algorithm. This n is a arbitrary integer of Z, and this m is the positive integer. Then division algorithm asserts that there exists unique q and r such that this n can be written as this mq plus r. Okay, where 0 less than or equal to r less than m. Okay, this is due to the division algorithm. Now you write what is a raised to n. A raised to n is equal to a raised to mq plus r. Okay, we substitute for this. And a raised to mq plus r can be written as a raised to m whole raised to q into a raised to r. Okay, that implies what is a raised to r here. By operating the inverse of this quantity on both sides, you can get a raised to r is equal to a raised to m whole raised to q inverse into a raised to n. When you apply the inverse of this on both sides, LHS and RHS, then this can be written as identity element. Then identity times a raised to r is equal to a raised to r, and the left side will be this times a raised to n. And we can write this as a raised to m whole raised to q whole raised to minus 1 can be written as a raised to m minus q into a raised to n. Okay, now we know that a raised to n is an element of H because of this. Okay, we take B belongs to H, the B is equal to a raised to n, then this a raised to n belongs to H. And we know that a raised to n, that is C, that is also an element of H. A raised to n belongs to H. Consequently, we can get a raised to m whole raised to minus q belongs to H. Then combining this a raised to n and this quantity are element of H, then we can get a raised to m whole raised to minus q a raised to n belongs to H. That means this a raised to r belongs to H. This is a contradiction because this r is less than m and a raised to r belongs to H. So this contradicts the fact that m is the smallest integer in Z plus such that a raised to m belongs to H. Okay, so we have already assumed that this m is the least positive integer such that a raised to m belongs to H. Here we can get a raised to r belongs to H, where r is strictly less than m. So that is a contradiction. Then this contradiction leads to the fact that this r is 0. Okay, if this R is positive, then we can get a contradiction. Then that implies R is equal to this contradiction leads to the statement R is equal to 0. Then we can get N is equal to N cube and A raised to N, that is our B. A raised to N can be written as A raised to M cube, since A raised to R is equal to 0. So A raised to R is equal to identity, R is equal to 0, then A raised to 0. We have A raised to M cube times identity, that is equal to A raised to M cube, which is equal to A raised to M whole raised to Q, and A raised to M is taken as this C, that is equal to C raised to Q, which shows that any element B belongs to H can be written as B is equal to some C power Q. This shows that H consists of the points C raised to Q, where Q belongs to Z. Okay, that means C is the generator of H, which implies H is a cyclic group. Okay, so this proves the theorem 6.6. As a corollary of the previous theorem, we can prove that the subgroups of Z under addition are precisely the groups NZ under and addition for N belongs to Z. That means we will observe the subgroups of Z under addition. Okay, so we start with the cyclic group Z. First of all, we can verify that Z under addition is a cyclic group because of this fact. The cyclic subgroup generated by 1 is Z itself. Okay, this consists of 1 raised to 0, 1 raised to 1, 1 raised to 2, etc., 1 raised to minus 1, 1 raised to minus 2, etc. So this is equal to 1 raised to 0 is the identity element of Z. So please note this, 1 raised to 0 is not equal to 1. This is a symbol which denotes the identity element of Z. So that is 0, and 1 raised to 1 is 1, 1 raised to 2 is 1, 1 raised to 2 is operate 1 2 times in this group, that is 1 plus 1, that is equal to 2, similarly 3, etc., and minus 1, minus 2, etc. Okay, so these are the elements of our Z, and due to this we can say that Z plus Z under addition is a cyclic group. Now we can verify the subgroups of this Z. Okay, so if we in order to take a subgroup, we can say that if H is a subgroup of Z, then the previous result says that H is also a cyclic group. Okay, H is a subgroup of Z implies H is a cyclic group. Okay, then we can say that this H consists of since if we the one possibility is H is equal to singleton set 0, so this can be considered as cyclic subgroup generated by 0 itself. 0 is the identity element. If H is not equal to singleton set 0, then H contains an integer. Okay, let it be some x belongs to H, that implies x belongs to Z, that implies x equal to 1 raised to something. Okay, 1 raised to some R, and if R is positive, then you can say that H contains a positive power of H. Otherwise you can take x inverse, that is equal to 1 raised to minus R. So from this fact you can say that H contains at least one positive power. 1 raised to n belongs to H for 1 raised to m for some m belongs to Z. Okay, now if we choose least such number as n, that is n is the least positive integer such that 1 raised to n belongs to H. This implies this H is equal to this cyclic subgroup generated by 1 raised to n by previous theorem, that is cyclic subgroup generated by n. This is nothing but this subgroup generated by n is consists of 0, that is n raised to 0, n, 2n, 3n, etc., and minus n, minus 2n, etc. Okay, this is what we called nz. nz means set of all multiples of n. So that form the subgroup H. That means any non-trivial subgroup H takes the form nz. The trivial subgroup is again cyclic, that is generated by 0. Okay, so this is the corollary 6.7. Okay, in the next class we will discuss some classification of cyclic groups, that means structure of cyclic group, and some interesting subgroups of finite cyclic group.